Hello everyone, welcome to lesson S3 on the differences between mass and weight. Now, first of all objects are made of tiny particles. That's part of the particle model that we've already talked about. But the definition of mass is the amount of matter or particles in an object. Now, if we think about a pencil has less particles than an elephant. Therefore, it will have less mass. Now, to measure mass, we do use the metric system, which means we measure it in kilograms, grams, or milligrams. But the most common way to actually measure mass is not in terms of counting the number of particles. Most commonly, we use a balance. Right? It's the most common measuring device for mass. Now, many balances actually compare the pull of gravity on an object being measured with the pull of gravity on standard masses. And so if they pull equally, then the masses must be equal too. Right? So if I know that this is 2 kilograms and it balances with this thing of unknown mass, well, if this we know to be 2 kilograms, then this one must be 2 kilograms, if assuming that they are balanced. And that's how they do it. But what they're really measuring is the pull of gravity acting on both of them. They're not actually counting the particles. It's just a comparison. Now, here's a key feature, and sometimes masses also are triple beam balances, such as this, where you slide things over to do the comparison. But key thing here with mass does not change no matter where the object is. An elephant would weigh lots more on Earth than on the moon. But the mass only changes when the matter is either gained or lost. So, for example, if we have this elephant, right, there's my elephant, and on Earth, and we were instantly transport that elephant to the moon, that elephant would have the same mass. So all the same particles are in this particular elephant. However, the weight is going to be different. It weighs more on Earth than on the moon. And the reason for that is because of force. Okay? Force is simply the push or pull acting on the object. Right? So if on Earth this has a push of gravity going down, and on the moon there is less gravity, you'll have less push downwards and therefore less weight. Now, the standard unit for force is the Newton, and we usually measure them with the spring scale. You can see some on page 300. The ones at school look something like this. Now, in order to describe a force, you need both its magnitude and direction. So its size and direction. A couple of examples of that: to lift a box, you might have to lift up 50 newtons upwards. Book falling your toe might exert a force of 15 newtons downwards. But either way, weight is simply the force of gravity acting on a mass. And we measure that in newtons in the standard metric, although in the imperial, this is where we also see things such as pounds. This is the like the U.S. system, the imperial system. right? The gravitational force between two objects depends on the distance between the objects and the mass of the objects. So you may be wondering, well, what objects are we talking about? Well, in the case of the elephant, this is object 1. And the Earth becomes object 2. Now on the moon, that elephant, I'll try to draw it about the same size, but no guarantees. So here we've got object 1, object 2. And so the amount of weight is dependent upon the mass of this object and how close they are. Now you may already be guessing that force of gravity actually exists between all objects of mass and all other objects of mass within the universe, which means you are actually gravitationally pulled towards the moon right now. Now, you don't feel it nearly as much because A, the moon is less massive than the Earth, and B, you are much further away from the moon than from the Earth. But all things wind up there. Therefore, an object's weight will actually change depending upon where it is. Right? We have a lighter weight in space because there's little gravitational force. Now, if you have not watched these two videos yet, these two videos were also included in the lesson on teams, so make sure you watch them. Watch me. Okay, make sure you watch them. The Eureka one does a really good job at explaining the difference between mass and weight. And the Veritasium one talks a lot about the kilogram. Now, I should note that in 2019, the definition of the kilogram was redefined to actually be fixed on the fundamental universe constant known as Planck's constant. Not what they were trying to do with the world's roundest object, but the concept is still the same in terms of what mass is. And so it's still a really, really good video. Now, Planck's constant is just the relation between energy and the frequency of a single photon of light, and should be there. Key thing, when going from mass on Earth, mass to weight on Earth, we're always going to multiply by 10. Now, this is, again, assuming Earth. If you're on Mars, if you're on Jupiter, if you're on the moon, you're at a different location in the universe, you cannot make this assumption. Only on Earth can you make this, and it's really just an estimate. So 20 kilograms becomes 200 newtons. Now, again, going from weight to mass, you're going to do the opposite. You're going to divide by 10. But again, you can only do this on Earth. So 450 newtons is the same as 45 kilograms. 82 kilograms is the same as 820 newtons. Where 38 newtons is going to be the same as 3.8 kilograms. And 37.4 kilograms times 10 is 374 newtons. Okay, one last little thing here. Which of the following is true of the mass and weight of the exact same person at two different locations? For example, Banff, Vancouver. A, B, C, or D? What do you think? The answer is, in fact, B. The weight changed, but the mass did not. So we've got some homework with this lesson. first of all, page 304, numbers 1 to 4, as well as the mass and weight worksheet. Please make sure you take a look at teams specifically for what is due when. And if you have any questions, let me know. Thanks for watching.